Hi, today we are reviewing exponential and logarithmic functions. So just as a reminder, exponential functions take the form of y equals a to the power of x, where a must be greater than 0 and cannot equal 1. Now this graph will have a y-intercept of 1, simply because anything to the power of 0 is 1. If a is greater than 1, our graph is going to increase as it goes to the right. If it's between 0 and 1, the graph will decrease to the right. The graph has a horizontal asymptote at y equals 0, and in some cases we'd have an a of e, which is Euler's number, which is 2.71828, and this number just continues forever. So converting between exponential and logarithmic forms, if we have something written as x equals a to the power y, it can be rewritten as log base a of x equals y. And we have common logarithms and natural logarithms. So if we have log x, so we don't have a base written, that's the same as log base 10 of x. And if we have a natural log, so ln x, that's the same as log base e of x. So for example, write the following in logarithmic form. So we have 3 to the power of 3 equals 27. So this would just be log base 3, so we always keep the same base, of 27 equals 3. This next one, 5 to negative 2 equals 1 over 25, so that would just be log base 5 of 1 over 25 equals negative 2. This last one, 4 to 0 is just equals 1. It's the same as saying log base 4 of 1 equals 0. Now we're going to go the opposite way. So write the following in exponential form. So we've got log base 7 of 49 equals 2. So like I mentioned, our bases essentially stay the same. We just switch what value we're equal to. So we've got 7 to the power of 2 equals 49. And if we have log base 4 of 1 over 64 equals negative 3, that just means 4 to negative 3 equals 1 over 64. Now, just like exponent laws, there's logarithmic laws. All of these require x to be greater than 0, y to be greater than 0, a to be greater than 0, and a cannot equal 1. So if we have our power law, which is log base a of x to the power of m, we can move that exponent to the front, and it becomes m times log base a of x. We have our product law, which says if we have log base a of x times y, we can break that up into log base a of x plus log base a of y. We also have our quotient law, which states if we have log base a of x divided by y, that can be broken into log base a of x minus log base a of y. And we have a change of base law, which is log base x of y is equal to log base c of y over log base c of x. Now, there is another couple properties of logarithms. We have log base x of y is the same as 1 over log base y of x. So essentially these two get reversed and we have 1 divided by that. And we also have a to the power of log base b of c is the same as c to the power of log base b of a. So we'll look at some examples. Our next example is expressed as a single logarithm and simplified. So we've got 3 times log base 9 of 6 minus log base 9 of 72. So we're going to use those log laws to help simplify this. So first thing I would do is use a power law to bring this 3 in. So this would become log base 9 of 6 cubed minus log base 9 of 72. I'll then to 6 cubed. So that gives us log base 9 of 6 cubed, which is 216, minus log base 9 of 72. Now, because we have the subtraction, we can use the quotient law. So that gives us log base 9 of 216 divided by 72. Now that gives us log base 9 of 3. Now we know that 3 can be written as 9 to the power 1/2. Now because we got these the same, our logarithm's equal to this exponent. So it's going to equal 1/2. Next, we've got log of x minus 4 log z plus 2 log y squared. So we'll deal with the power law first. So we've got log of x minus log of z to the power of 4 plus log of y squared, and then we're squaring it. So that would be y to 4. Now, anything that's positive we can combine with our addition law, and the negative will take care of with our quotient law, so this becomes log of xy to 4 over z to the power of 4. That's when we're simplifying 7 to the power of log base 7 of x. We're going to use one of our laws, so we're just going to utilize our a to log base b of c equals c to the power of log base b of a. So when we do that, that makes this x, x log of 7 of 7. So that'd be x to the power of 1, which is just going to equal x. Now we have e to the natural log of 4. Now that's going to be the same as 4 to the natural logarithm of e. The natural logarithm of e is 1, so that's just going to be 4. Now we've got 1 over log base 4 of 10 plus 1 over log base 25 of 10. So for that, we're going to utilize our log base x of y is equal to 1 over log base y of x. So therefore, we can rewrite this as log base 10 of 4 plus log base 10 of 25, and then use our product law to combine those. So we'd have log base 10 of 4 times 25, so 100. Now that's the same as log base 10 of 10 squared, so that's just going to be 2. A bit more of logarithmic functions. If we have y equals log base a of x, a has to be greater than 0, a cannot equal 1. Our graph of y equals log base a of x will have an x-intercept of 1. And if a is greater than 1, our graph increases to the right. If it's between 0 and 1, it decreases as we go to the right, and has a vertical asymptote at x equals 0, because if you recall, a logarithmic function is the inverse of an exponential function. So all of these are the inverses of our graphs of exponents.